Welcome to Geology, everybody. For our next plate boundary, we're going to do another convergent, this time continental, continental. What happens in this scenario? And we'll start with another drawing. What we got a long time ago, pre-human, floating, well, not floating, but in the ocean over here on its own, would have been an island that would one day be called India when humans evolved and started naming things. In between India and another continent that would one day be called Asia, there was a sea. At the sea, I believe they called it. Whoop. That might be a purple ocean, but it's all good. India is moving that way and at a pretty good speed towards Asia. Now, where are we talking here? Let's go to Google Earth. This would be the way I'm drawing this. Going back, I mean, we're going back in geological time, a great amount of time, right? India would have been back over here and Holland that way up towards Asia until eventually they hit. Now, if you've really started to get these tectonic boundaries down, you might be saying to yourself, well, what about this ocean crust right here? Something's got to happen. And you're right. As India's moving forward here, we'll draw it progressing a little further on its trip. As it's going forward, this oceanic crust has to go somewhere. It has to get consumed. I'll leave Asia right about where it is. And you'd be right if you could spot that this would have been a subduction zone at the time with that thinner oceanic crust being subducted down underneath. Just like what we see today, and you should know this by now if you've made it this far in the videos, along like the west coast of South America with those subduction zones, right? Also keep in mind this idea of like thicker continental crust, thinner, more dense oceanic crust. Because what's going to happen when they finally hit, is that they're too buoyant to subduct. They're not going to get sucked down into the asthenosphere. They're going to ram into each other. So I'll draw a thicker continental crust right here. I'll label it India again because now there are humans that name things. And it hits and it makes this big mountain range. Like if two cars hit each other head on, the hoods get all kind of crumpled up. They're shorter but taller, right? Same thing here with the rock. Over on this side, Asia. Let's go back and think about that isostatic balance thing we talked about too. If you got this big mountain range that you're building up on this like mushy layer of the asthenosphere, the mattress example I used back then works here too. If you sat on a mattress and you didn't sink in at all, it would be weird, right? If you build a huge mountain range on top of a softer layer down below, and it didn't move, it would be weird. It does. It sinks down in a bit. So mountains like this not only are like the tallest places on Earth, but they're the thickest with the crust in the lithosphere. It's continuing to go. It slowed down. I found a picture just for the sake of it, just to see what we're doing. Again, this would be map view, looking down from the top, and what we're drawing here is the cross section. This is if I could cut into the Earth and look at it from the side. In here, I mean, everything's going to be all banged up. So this quote is like this gentleman writes popular geology books, not like technical ones, nature books as well. But if he said, like, basically, if I had to take all of this that I've written and break it down into one sentence, the summit, the top of the tallest mountain, is marine limestone, rock that formed below sea level. So if we can have rock forming below sea level here, fossils and all, that once this car wreck happens, once this collision happens, that rock gets lifted to very high altitude. What, 8-9 kilometers up, somewhere on there? Down deep where there's a lot of heat and pressure, later in the year we'll be talking about metamorphic. We'll think about where that's happening in this scenario. But for now, there it is, our thickest part of the crust. Going back there, I'll just switch back to north up so that we can... That's it. So this is heading into the continent of Asia, giving us really this whole entire plateau with that like front range of mountains right through there. Very, 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 very tall mountains. Now, a trick of geology, then, if as we get deeper in the semester, is to think about where maybe has this happened in the past. If we know what that looks like today, what the results of continents coming together are, what would it look like in the past? Which is kind of like saying the same thing as, what if we were to cast this forward into the future, a couple 100 million years, and erode off the top? All of that limestone at the top will get weathered and eroded. I mean, and that's happening today, right? Let that run forward for a couple 100 million years. What would the roots of this thing really look like? And how might that be similar to what we see historically, where like maybe other mountains have formed? If you've been through the Appalachians, they're still pretty big mountains, but not nearly as big as they were back when the collisions that happened that caused these things. And now we're seeing what that might look like after it's worn down for a long, long, long time. All right, what do you think? That should do it. So just to make sure we get the spots in the notes, this makes a big mountain plateau. The type section absolutely is the Himalayas. It's like that's the textbook spot where this is happening today, and continental to continental collision because of compression, and hopefully that does it. So we'll move on to transform faults and call it good. Thanks everybody. We'll talk to you soon.